Hello. Moving further with our second chapter, today we will see about the potential energy in an external electric field. Okay, simple one. Potential energy in an external electric field. In that, the first case is, we have two cases. First case is potential energy of a single charge. So when we consider single charge, what is the potential energy? In our previous discussion, we have seen the potential energy, or how do we represent that potential energy of a charge? We represent it by U, and regarding the formula. Now the difference is that we have external electric field. So when you have the external electric field, what is the potential energy of a system or single charge? Next case we will see more charges, two charges or two or more charges, like that. So first is single charge. So the main difference is that you have some external electric field E in one area. Get the single charge from infinity to the particular place where you have external electric field and calculate the work done in bringing the charge from infinity to that point. Okay. What do we assume here? Here we assume is that the potential at infinity is taken to be 0. That means V infinity is taken as 0. When you bring the charge to the place where you have the external electric field, what is the potential energy of that single charge? That is what we have to find out. So this electric field E, external electric field E, will produce its own range, correct? It will have its own range. So when you bring the charge from infinity to this place where you have the external electric field, the potential energy of that system is represented as Q into V of R. Okay, this is how the equation is. Q is the charge that you are bringing. V of R, that is the external potential at the point R. At the point R, in the sense, any origin you consider, bring it, suppose this is the origin, you bring it here. If you are bringing the charge here from infinity to this point, so it is represented as V of R. What is the potential here? So the charge multiplied by the potential will give you the total potential energy of that single charge. This is very simple one. So Q into V of R. Okay, I hope this is clear. Very clear explanation is given in your textbook, that is NCERT textbook. Go through it, which I have explained it earlier, the same concept you have, and only the thing is this equation is extra. Okay, what is the potential in that position, then multiplied by the charge which you are bringing from infinity. So this is the potential energy of a single charge. Next is potential energy of a system of two charges. Instead of one charge, we will consider two charges. System of two charges in an external electric field. That is the same thing. So when you have two charges or two charges, if you are bringing from infinity to an external electric field, the total potential energy is, we have to use superposition principle. Superposition means adding all the potential energy of each charge. Okay. So now how you will find out? Suppose say that you have charges Q1 and Q2. Say that you bring this one R1 and R2. That means this is a position vector. That means this R2 is at a Q2 is at a distance of R2 from Q1. Okay, that is a simple concept that we consider. Two charges we will consider, and the position vectors are R1 and R2. Now when you don't have this one, first we will bring only the first charge Q1 and R1. As we have calculated in the previous one, so what should be its potential energy? It has to be Q1 into V R1, correct? Q1 into VR1. That is the first one. V of R1 is the potential. So this is the first you consider. Let it be like that only. Now bring the second charge into picture, Q2. Now what has to be done is work done on Q2 against the field due to Q1. So you have already Q1 present here. Bring another charge Q2. What you have to do now? You have to do some extra amount of work in bringing this Q2 near this point Q1. Why? Because this Q1 is already in the external electric field and that will always oppose bringing some more charges. So you have to do some extra amount of work in order to bring Q2 in this range, or which is at a distance of R2 from Q1. I hope this is clear. Sorry, you have Q1 that will have some force or energy within it. It will oppose the bringing of one more person. Okay, so you have to do some extra amount of work. So now when you are bringing this, let it be like this only. When you bring the another charge Q2, you have to do some extra amount of work, that is Q2 into V of R2. At the end we will add using the superposition principle. So now it is Q2 into V of R2. What it will be? It is Q2 Q1 divided by 4 pi epsilon naught into R2. R2 is the position vector for the second one, or distance between Q1 and Q2. So this V of R2 is created by the charge Q1. So you have Q2 Q1 divided by 4 pi epsilon naught into R2. Or you can write it as R12, so that you have a distance of Q1 and Q2 as R12. Okay. Now you have these three. Find out the total potential energy of the system. So work done in bringing Q2 to R2 will be this much now. This much. So you have to add here these two. This is the potential required. This is the total potential. Now when you are considering this Q1 also, because we are considering two charges, this much is only for Q2. Okay. When you add all these three, you will get the total potential energy of the system of two charges. So that means the total work done in assembling all these charges or the two charges is given by the configuration of, or you have to add these two. These three equations you have to add. So the total potential energy, let me represent it as U as usual, V of R1 plus V of R2 plus Q1 Q2 divided by 4 pi epsilon naught into R12. I will write it as R12 so that it is clear for you. That is, it is a distance between the charges Q1 and Q2, where V of R1 is the potential at the point and V of R2 is for a potential at another point R2. And now when you add all these three using the superposition principle, you get the total potential energy of system of two charges. Okay. Look in the, after this concept you have an example sum in your textbook using the same concept. Please solve that. Okay. Then only all the concepts will be clear. You have to solve all the numericals based on all the concepts. Example numericals are also very important. So please go through it. So this is regarding the potential energy in an external electric field. Now next is the important one. It is the potential energy of a dipole in an external electric field, which is very, very important. So when you have a dipole, what do you mean by a dipole? Two equal and opposite charges. Correct? So it is potential energy of a dipole. Very important derivation. in an external electric field E. Dipole in an external electric field E. So we will consider the very small derivation, but it is very important. Let this be the direction of the electric field. Place a dipole plus q and minus q. What should be the distance of separation between them? It has to be 2a. Say that it is making an angle of theta. Let this be the center. So what this has to be? This will be a, this will be a. It has to be a cos theta. I will not represent it again. Drop a perpendicular here. You get 90 degree. This will be the hypotenuse. Cos theta is adjacent by hypotenuse. So cos theta is equal to this distance divided by hypotenuse. So this distance you get it as a cos theta, or the foot of the perpendicular is a cos theta. That is a cos theta. Okay. So now what will be the direction of the dipole moment? Minus q to plus q. Let me consider this way. This is easier. Minus q to plus q. This will be the direction of the dipole moment always. Now, when you have this one, say that here you have Fe, F into Q, or here Q into E. QE is in this direction, here QE is in the opposite direction. That is the force at this point. So these two forces will make the dipole to rotate in the external electric field. So that is what we call it as torque tau. This we have studied. So torque tau. What is the equation for the torque tau? Q cross E. Correct? So external, when you have the dipole in an external electric field, so you have P cross E. What is P? Dipole moment. So it is nothing but what? PE sin theta. Tau will be equal to PE sin theta, cross product, where theta is the angle made by the dipole with an electric field. That is theta. Now, when say that you have two angles, one is theta naught and another one is theta 1. You have some field or external torque, extra torque or extra force you are creating here, such that it keeps on rotating between these two angles, theta naught and theta 1. Theta naught and theta 1. Now you have to calculate the total amount of work done in moving from theta naught to theta 1. So that is what we do in calculating the potential energy, because potential energy is nothing but the external work done. So tau external of theta into d theta. So total work done will be integral of tau external of d theta from theta naught to theta 1. So you have take two angles from theta naught to theta 1. What is the external work done is what you have to calculate. So just integrate this one. I'll write it again here. Theta naught to theta 1 of tau external of theta into d theta. It is nothing but theta naught to theta 1, or theta also you can take. Tau external is nothing but PE sin theta into d theta. Integral of sin is minus cos. So minus PE cos theta from theta naught to theta 1. So we will get it as minus PE cos theta 1 minus of minus is plus PE cos theta naught. So W is equal to PE into cos theta naught minus cos theta 1. Or if I have taken theta, it is just a theta. So PE into cos theta naught minus cos theta. So this work done is stored as potential energy. So please note that this is taken as potential energy. So you can take the angle wherever you want. If you want to take the initial one as 90 degree, so that means if you are placing the dipole like this, theta naught is 90 degree. So cos theta will be 0 and it is theta. So what you will get if theta naught is equal to pi by 2? You get work done is equal to minus Pe cos theta. So initially if you are placing the dipole like this straight or perpendicular to the electric field, then work done or the potential energy which is stored in the system will be minus Pe cos theta. So minus Pe cos theta can be written as what? Minus P dot E. Very important equation. So this is nothing but the potential energy. You can write this W as U also. So it is minus P dot E. This is the equation for the potential energy which is stored in the dipole. So under this you have three important conditions. First one is stable equilibrium. Using that only. Stable equilibrium. What do you mean by this stable equilibrium? When can you tell that the position of the dipole is stable equilibrium? When theta is equal to 0. When theta is equal to 0, what will be the work done? It is cos 0 is 1, so it is minus Pe. So we tell that the dipole is in stable equilibrium when theta is 0, or if this is the direction of the electric field, when you are keeping the dipole in this way, then you get work done as minus P dot E, or it is nothing but Pe. The next one is position of zero energy. When you get the position of zero energy, again if theta is equal to pi by 2 or 90 degree. So first you are placing there only the dipole like this. So initial is taken as 90 degree. You turn this and again bring back. Again it is 90 degree. So work done will be 0. Cos 90 is 0. So work done will be 0. So we tell this as position of zero energy. Okay. So theta is pi by 2 is taken as position of zero energy. Next is position of unstable equilibrium. Here the potential is maximum. So when you get the unstable equilibrium, we get the unstable equilibrium when theta is equal to 180 degree or pi radians. So cos pi is minus 1. So work done will be maximum Pe. Cos pi is minus 1. Minus of minus will be plus. So work done will be maximum. So in this case we tell that the dipole is, potential energy of the dipole is maximum when its dipole moment is anti-parallel to the external electric field. This is called as unstable equilibrium. This is unstable equilibrium, position of zero energy, and the first one is position of stable equilibrium. In that case, the dipole moment is along the direction of the external electric field. Here the dipole moment is opposite. Here it is aligned perpendicular. So these are the three important conditions using the equation of the potential energy of a dipole in the external electric field. Okay. This is about the potential energy in the external field. So these are the three important points. Solve it clearly. Practice all the equations and then try to solve the example numericals. Thank you.